This video is about the kinetic molecular theory and the ideal gas law. So if you remember, um, for the kinetic molecular theory, we made several assumptions. Number one, that the gas particles are dimensionless, so they are very small compared to their distances. Number two, that when they collide, there is a completely elastic collision, meaning the kinetic energy is conserved, meaning because you might be saying, sir, if I have a particle, which is a gas particle inside the container, when it hits the walls, would it not lose energy and after a while not move, right? So this is what we are trying to prevent. So we are trying to assume that they will never lose their kinetic energy. So kinetic energy is conserved. Number three is that no repulsion or attraction force is existing between two particles, two gas particles that are inside that container. And again, that is also kind of related to here because if they are very small, so when they get past each other, they don't really feel each other. There's no attraction or repulsion. And then number four, that the temperature is related to the kinetic energy of particles. And again, when particles are very moving, very fast moving, the temperature is higher. And then when the particles are slow moving, the temperature is lower. So all of these assumptions, class, are actually what makes an ideal gas. This is why you have the ideal gas law. So when you say ideal, meaning model gas, so it's really a hypothetical gas. It's not a realistic gas that you can find anywhere. So that means, again, just like what I told you about scientific concepts, this is a simplification, a perfect idea of a gas that follows all this. In reality, um, gases do not follow the ideal gas at some cases. For example, if you have very large gas particles, for example, if you have octane, remember octane gas is, or uh, octane gas is, or decane gas is 10 carbons, right? So it's very long molecule. So the molecules now are so big that you cannot anymore assume that they are dimensionless. So they do not follow anymore the ideal gas law. Okay, so again, this is just a simplification. And then collisions are elastic. So for example, if you place the gas particles inside a very stretchable material, uh, at some point the elasticity, I mean the property of the material kind of absorbs some of the particles in the some of the energy, kinetic energy of the particles inside the gas, and so this is not followed anymore. And no repulsion or attraction. This also comes into bigger particles. If you have big particles, then the more likely they are going to be attracting or repul or repelling each other. And also the temperature. So again, the bigger the particles are, then the more kind of other factors would come in, and so you will not have an ideal gas. So just a heads up, the ideal gas flow, it's kind of really applicable to very small gases such as helium, such as carbon, argon, or krypton, or carbon dioxide, or oxygen gas, nitrogen gas, those small gases. But the bigger the gases become, the bigger molecules, uh, when you have gases that have bigger molecules, more likely than not, they will not follow the ideal gas law. So again, it's kind of like we have discussed ideal gas law, and if it sounds like it's the ultimate law, but in reality, again, reality is stranger than concepts. So therefore, concepts are really simplifications of things, and in reality, there are actually other factors that you consider. So, for example, if you have gas particles that are spread out, at first they are spread out, and at first they follow like the ideal gas law. But the moment you kind of compress them closer to each other, if they get so close to each other that the distances are now, if the container is so small that the distances are now smaller, are now kind of not that large compared to their sizes, then it starts to not behave like an ideal gas. So the ideal gas law, although it's a very useful law, you kind of only apply it when it's applicable. So when the gas is kind of farther apart, when the gas particles are so small, and so on and so forth. So again, just a heads up that although it's it's kind of easy in the head to think that it's easy in your mind to think that you have these laws in nature that gases would follow. In reality, there are other many different factors that come in play, and um, you cannot really control all the other factors. But again, um, we cannot also saying, sir, if that's the case, if the ideal gas law does not apply to everything else, only small gases, then why study about it? Again, that idea does not work, because what you do is you kind of have the simplest concept, which is these assumptions, and then the moment you study complicated molecules, like for example, how do bigger molecules, gases with bigger molecules interact, that's the time when you kind of get the ideal gas law, kind of modify it to fit the current situation. You don't scratch this just because it doesn't apply to everything else. Because if you do that, then you don't develop any theory at all, because no theory applies to everything, right? So there must be a case to case basis. So it's good that we kind of have a basic idea of what it is in the simplest configuration, which simplest configurations, meaning we kind of simplify everything. That's why we have these assumptions, and then from there we can work on into building other theories that apply to more complicated situations. But that's the connection between the kinetic molecular theory of gases and the ideal gas law. So basically, what the kinetic molecular theory of gases is talking about is an ideal gas. It applies to ideal gases. But again, the moment that gases would have bigger molecules, the moment gases would have other circumstances that they're like they are in a container and they are already closer to each other, such that some of these assumptions are not valid anymore, they start to not behave like an ideal gas. But for the most part, they do. As long as they are small, as long as the spaces in between them are kind of bigger, as long as you don't have other conditions that kind of invalidate these assumptions. So these assumptions, although there are four, most of the gases or the gas setups that we have fall. I mean, is a situation where we can use these assumptions, but some of them do not cannot be, some of these assumptions cannot be valid for some situations. So that's just a heads up. So that's the idea behind the kinetic molecular theory of gases and how it's related to the ideal gas and ultimately the ideal gas law.